This is a CCEA GCSE Further Maths Mechanics paper, and it's from summer 2021. So let's take a wee look then at question 1. A particle rests in equilibrium at a point O on a smooth horizontal plane. The particle here, is acted upon by 3 horizontal forces of magnitude 18, 28 and P. The direction of each of these forces relative to the horizontal axis OX and OY is shown below. The particle remains in equilibrium. Calculate the value of theta. So because it's in equilibrium, it means everything going this way equals everything going this way, everything going this way equals everything going this way. So we're going to resolve this way here, and because we know the 14 there and we know the 28, the only unknown is going to be the theta. So resolving this way, so going this way is going to be 28, and going across that angle then is going to be cos theta, and that gives 14. That means cos theta is 14 over 28. That means theta is cos to minus 1, 14 over 28, and if you put that into your calculator, you'll get 60 degrees. Calculate the value of P. So to do that, then we're going to resolve up and down. So again, everything going up equals everything going down. Let's see what we're going to have. Here, the 28, we're going to resolve it this way. So we're not going across the angle here. So it's going to be sine. So 28 sine theta. And we know theta, of course, so it's sine theta, so sine 60. And that equals then P, because that's the only force then acting down. So we just plug that into our calculator. P is 28 sine 60. You put that into your calculator, then the 2 decimal places is 24.25 newtons. Question 2. Two forces A and B are defined by A, which equals 2I minus 4J, and B, which is xi minus 5J. Write down an expression for the resultant force of A and B in terms of I and J. So the resultant of A and B is we add the I parts together, so we're going to have a 2 here and an x. So it's going to be 2 plus x I, remember to underline your I, plus, that's minus 4 minus 5. I shouldn't have written plus there, so obviously I've written minus, so it's going to be then minus 9j. The magnitude of the resultant force of A and B is 15. Calculate the 2 possible values then for x. So the magnitude of the force is like the length of the line, where we have the I bit going along here, so it would be, this would be our I going along here, and this would be our j in this case because it's in a minus 9, and that's then going to be 2 plus x. My diagram's awful here. And we know then the magnitude, which is the length of this line, would be 15, so we need to use in Pythagoras for this. So it's going to be 2 plus x squared plus 9 squared equals 15 squared. If I multiply out my then 2 plus x, so remember we've got to use FOIL here, so it's x plus 2 upon x plus 2 plus 81, and then 15 squared is 225. So that of course gives me then x squared, outer and inner, is plus 4x, last is 4, plus 81 is 225. Rearrange all this, we get x squared plus 4x minus 140. So where am I getting that from? That's the 4 plus the 81 is 85, and then take away the 225 from both sides, then equals 0. That factorizes reasonably straightforwardly. So we would have then x plus 14 and x minus 10. So that means obviously x is equal to minus 14, or x is equal to 10. Question 3. A sprinter running in a 100-metre race took 12.5 seconds to complete the race. He accelerated uniformly from rest to a maximum velocity of 9 metres per second in 2.4 seconds. He maintained this velocity for the further 7.6 seconds. He then decelerated uniformly to a final velocity of v in the final 2.5 seconds. Draw a velocity time graph of the sprinter's journey on the axis below. So he started from 0 and went up to 9, then in 2.4 seconds. So something then that looks like this, obviously acceleration, and you can see the gradient heading up like that. And we would want to mark that off then as a 9, so we know it's a 9 there. We should really have done a dotted line there. And then going down here, that's then at 2.4. He maintained this velocity for the further 7.6 seconds. So with 2.4 and then a further 7.6, 2.4 plus 7.6 of course takes me to 10. And so that's then my 10 there. He then decelerated uniformly to a final velocity of v in 2.5 seconds. So down here then he slows down to some speed that's v. And my time there then is 12.5. And if we do a dotted line going across here, that's my v there. The first part, sorry, that was the first part, is to draw your velocity time graph. Again, I have all the information in there. I have my 3 times 2.4, 10, 12.5, and then my 9, which is hard to see here, and the v there. Calculate the distance travelled in the first 10 seconds. So distance travelled, I hope you know then, is the area underneath the graph, and so we need the area of up to here. So we need the area of this rectangle, and we need the area of the triangle. So let's write that. Distance is equal to, I guess let's go for area of our triangle plus area of a rectangle. So reasonably straightforward here. We are going to go 2.4 times 9 divided by 2, a half upon 2.4 upon 9. And then this here, so that's 9, and that is 7.6. Again, put those two things into your calculator, and you get an area then of 79.2, and that's 79.2 meters. So we have that. Part 3, find the value of v. So the value of v we can work out because we can find the area of this trapezium. So we know it's a 100-meter race. The area of this is 79.2. That means they still have 20.8 to go. So where am I getting my 20.8 from? Because when it's a 100-meter race, so it's 100, take away 79.2, which then is 20.8. That means the area of this trapezium here must be 20.8. So our area of a trapezium is a half a plus b upon h. And so it's a half. These are the two parallel sides. Two parallel sides. That's a 9 and that's a v. And then the height is 2.5. So we're going to have half upon 9 plus v upon 2.5, and that gives 20.8. So whatever way really you want to do that, that's going to be 1.25. A half times the 2.5 gives me 1.25. 9 plus v is 20.8. You could multiply out your bracket. I'm just going to divide by the 1.25. 9 plus v. 20.8 divided by 1.25 is 16.64, and take away 9 for both sides, I get then 7.64. So my value of V then is 7.64, and that's the speed. So it's in meters per second. Find the sprinter's deceleration in the last part of the race. You can do it a couple of different ways. You could find your gradient. So the gradient of that line there is going to be giving us our deceleration, or we could use UVAST. So I'm going to use UVAST, and hopefully we can get enough information in from there. U, V, A, S, and T. U, so at that part of the journey, the initial speed was 9. V we've just worked out was 7.64. The distance they travelled was 20.8, and the time taken is 2.5. So we know all those things. We're coming down with information there, really. So we're going to use V equals U plus AT. And we have 7.64 equals 9 plus 2.5, which is my time A. So my 7.64 take away 9. So that gives me 2.5a. I've sort of flipped this around, I hope that's okay. Is minus 1.36. And a then if I divide minus 0.544. So that's an acceleration of minus 0.544. Notice they've asked for deceleration, and I've even put it in bold to remind you, therefore deceleration is 0.544 meters per second squared. This question 4. A block of mass 7 kilograms is held at rest on a rough horizontal roof. It is connected to the block of mass 9 kilograms by a light inextensible string which passes over a smooth pulley attached to the end of the roof as shown in the diagram below. The 9 kilogram block hangs freely. The blocks are released from rest, and after 2 seconds they're both travelling at 4 meters per second. Calculate the acceleration of the blocks. This one is going to be UVAST to start with. I think that's quite hard to see. Quite often you do F equals ma for these, but they've given us the information. We're going to start with the acceleration, then I assume we'll use F equals ma a little bit later on in the question. So U, V, A, S and T, and as ever we're looking for 3 pieces of information. If we know 3 of these, then we can work out all the rest. It says the blocks are released from rest, so we know U is 0. After 2 seconds, so time is 2, they're both travelling at 4. So there's our 3 pieces of information. Find the acceleration. V equals U plus AT. 4 equals 0 plus 2a. So A is 2. So put that down there. A is 2 meters per second squared. Find the tension in the string. So for that we could use, I guess, a couple of different options, but I think we're going to have to use F equals ma then for this. So it's maybe worth putting on what forces we're going to have. This is a rough surface, so there's going to be a friction acting this way here. There is a 7g acting down. We don't always need to put that in. 7g, and then there's a normal reaction R. There's a tension coming out of this. There's things acting in the pulley. We'll leave those. We don't need them. There's a tension there, and then there's a 9g. And we also know the acceleration is going this way here. So we do our double arrow like that. Our double arrow like that. So we're going to do F equals ma then for this block here. So it's a 9 kilogram block. F equals ma. I often do the right hand side to make myself feel better because it's a bit easier. The mass is of course 9, and the acceleration we worked out in the first part, so it's 2. So that's just 9 times 2, and then this F indicates any forces that are affecting the acceleration. So this is making it go quicker, this is making it go slower, and it's going this way, so this ones are positive. So it's 9g take away t. 9g take away t. Sorry, I'm not sure. I got mixed up there. I was about to tell you that g was 10. I'll put in that instead. 9g take away t equals 9 times 2. So 9g, which is 9 times 10, so that's 90 take away t is equal to 18. And of course then if you rearrange that, we can do whatever way you want. Add t to both sides, take away 18 from both sides. You're going to get t is 72. So t then is 72 newtons. The force due to friction acting on the 7 kilogram block. So again, we're now going to do F equals ma for the 7 kilogram one. F equals ma. So let's take a look again at our diagram. What forces are affecting the acceleration here? There's a T, that's what's making it accelerate, the tension in the string, and then take away the friction. And we've been asked to work out the friction. Now remember, we know the T, we've just worked it out, so that should make it doable. So again, right hand side is going to be the mass, which is 7, the acceleration then is 2, and then the tension in this one, so it's T, take away our friction, is 7 times 2. 72, which is our tension, we're just taking it from up here, take away friction is 14, and rearranging that then, our friction is going to be 58. So down at the bottom then, friction is 58 newtons. On to question 5. A block of mass 6 kilograms is held at a point A on a rough slope which is inclined at an angle of 28 degrees to the horizontal as shown in the diagram below. The block is projected up the slope from a point A at a speed of 4 meters per second. Mark on the diagram above the 2 other forces acting on the block. So if it's being projected up, then there's a friction going down. I think this question's worded very slightly strangely, because if it's projected up, I guess there'd be a force pulling it up, but it's not asking for that. And the other thing, of course, then is going to be our normal reaction acting this way here. So that's your other 2 forces. The block comes to rest at a point B where the distance AB is 1.25. Calculate the deceleration of the block as it moves up the slope. Again, this can be confusing. In this scenario, they've given us enough information, so we're finding the deceleration, so we're going to use U vast for that. U, V, A, S, and T. Calculate the deceleration of the block up the slope, and we know that it comes to rest. So we know V is 0. It's projected up the slope at 4 meters per second. So that's our 4, and then our S then is 1.25. We have V, we have U, we have S, and we want A. So we're going to use then V squared equals U squared plus 2AS. 0 U squared, so that's 4 squared, which is 16, plus 2 upon A upon 1.25. 2 times 1.25 is 2.5. So 2.5A is minus 16, and A then is minus 6.4. They have asked again for deceleration, so just be careful that we put in then a positive 6.4 in like that. Hence, show that the force due to friction acting on the block is 10.23, correct to 2 decimal places. So we're going to have to find then this frictional force here, and we'll have to show it's equal to 10.23. So it's being projected up the block, so we're going to do F equals ma heading in that direction there. And it's parallel to the slope. So what forces do we have that are affecting this? There's nothing pushing it up, so there's just a friction which is going straight down. That's the direction we're resolving, and there's also our 60. So our 60 along the slope, or we rule is sine slope, if that's the 28 degrees there, so it's going to be 60 sine 28. So we will have minus 60 sine 28 minus friction, because they're both going the other way. We're taking this direction here. This is the direction of motion that's going up. So we're taking this direction here to be positive, and so we go then the other way, and then that equals mass times acceleration. The mass of the block is 6, and the acceleration we've just worked out is minus 6.4. Remember, it's not deceleration we're putting in there, it's the minus 6.4 is the one then that we want. So our friction then, I would take this over to this side and then this over to this side. 6 times 6.4 is going to be 38.4. Take away 60 sine 28, and that's what our frictional force in there. Hopefully you're okay with the rearranging there. And then if we go 38.4, take away 60 sine 28, it gives us 10.23, which is obviously what we wanted. It was good of them to give us that value. So friction then is 10.23 newtons. From rest at B, the block now slides down the slope. So it's made its way up to B, and now it's going to slide back down again. The magnitude of the force due to friction remains unchanged. Calculate the new acceleration of the block. So we now have different forces acting on this here, and now the friction, which is 10.23, is acting this way here. Our normal reaction is still here, and that's okay. So it's sliding back down. What makes it slide back down? It's this 60 sine 28, and then take away our friction. So again, we do F equals ma for that. I'm doing that parallel to the slope. So as I said, that's 60 sine 28. Take away, it's the friction, so it's 10.23. However, it's much better if you can use a more accurate one, so I'm going to do an extra decimal place. That's 10.232. And that's equal to our mass times our acceleration, and then the acceleration is what we're trying to work out. So if you put that into your calculator, let me see. I think our 6A comes to something like 17.9366, and then my A is 2.989, which for us then is going to be 2.99, and they have the units in there for you anyway, so you can't quite see that. And then finally, the speed of the block as it passes the point A. So what do we know about it? It started from here and it's heading down to here. We know it started from rest there, and that distance there is our 1.25. We know that from before, and we now have our acceleration. So we should be able to work out what we need. U, V, A, S, and T. U is 0. Speed of the block as it passes A is what we're looking for. Our acceleration, as we know, is 2.989, and our distance then is 1.25. U, V, A, and S. So we'll be using V squared equals U squared plus 2AS. V squared equals 0 squared plus 2 upon 2.989 times 1.25. 0.989, let me see. I think we get 7.4736. And then take the square root, and we get 2.73. That's our final calculation required, so we don't need to go with any more accuracy. 2.73. Question 6. A uniform rod AB of mass 30 kilograms rests horizontally on two pivots, one at A and the other at the point C is shown in the diagram below. The point M is the midpoint of the rod. The distance AC is 1.2. The reaction at pivot C is twice the reaction at pivot A. Mark on the diagram all the forces acting on the rod. So first of all, we're going to have our 30G and it acts through the midpoint. And then we're going to have two R. So normally we go R1 here and R2, but we know them. We know what the size compared to each other. The reaction at pivot C is twice the reaction at pivot A. So I'm going to call this one R. And I'm going to call this one 2R, obviously, because it's twice the size of the other one. Calculate the reaction at pivot A. We know everything going up equals everything going down. So we know then R plus 2R is 30G. We know 3R is 300. That's 30 times 10. And that means R then is 100. So R is a reaction at A. We've been asked for the reaction at A. And it's 100 newtons. On the next part, show that the length of the rod is 1.6 meters. So we're going to need to take moments then about a certain point. So I am going to take moments about the point A, and let's see then how it works out. So what distances do we know? I'm going to call this distance here X. And whenever I work out X, which is what I'm hoping to do by taking moments about A, then if I double it, that's obviously going to be the length of the rod, because this here is the midpoint. Okay, the other distance they've told us that AC is 1.2. So let's set up our moments then. As we say, we're taking moments about the point A, and our clockwise moments equal our anti-clockwise moments. So as I normally do, I put my, so here, the pivot is here, so I put my finger here, and then I just move in the direction of the arrow. So this one I can see is taking it clockwise. So that's going to be X times 30G. And this one's taking it anti-clockwise, hopefully you can see that. That's there. And we know that that's 200 because we worked out that R was 100. Let me see, so that's going to be a distance of 1.2 times 200. So it's going to be 300x and then 1.2 times 200. Sort of thing I should know is going to be 240. So X is 240 over 300, and then that gives me 0.8 meters. So our length then, as we know, is 2 times X, which gives me the 1.6, which is then what we were asked for. A mass of 18 kilograms is now attached to the end B of the rod. Calculate the new reactions at pivots A and C, given that the rod remains horizontal and in equilibrium. So I'm going to draw a new diagram then for the rod. So there's the old one there, we can just about see it as I draw this in, and we'll see then what we have acting on each of these forces. So because there's a new force, it means the reactions then will change. So that's our point A, that's our point C. So I'm going to call this one R1, I'm going to call this one R2. We still have our 30G acting down, and we now have a new 18G acting this way here. So we've been asked to work out R1 and R2. What we always note is that everything going up equals everything going down. R1 plus R2 equals 30G plus 18G. So obviously that gives us R1 plus R2. 30 plus 18 is 48, then times the 10 is 480. I'm going to do the same thing again. I'm going to take moments about the point A. And the reason I'm doing that is that eliminates the R1 here. Because I'm putting my pivot in here, then there's no moment then for the R1. If I push that direction, then it doesn't rotate. So R1 has no effect. There's no distance away from the pivot point. So it's going to be clockwise equals anti-clockwise. And so again, then my distances, so what am I going to have? There's two of them going clockwise this time. The 30G turns it clockwise, and the 18G turns it clockwise. So it's going to be that distance, which is 0.8 times 30G plus 1.6 times 18G equals, remember this is 1.2 times R2. So that's 300 then times 0.8. So obviously 240. 1.6 times 180. So I think then it's 288. And that equals 1.2 R2. So R2 then is 528. Sorry, 1.2 R2 is 528. So then R2 is 440 newtons. So our reaction here is 440, and now remember they both add together to give 480. That means our R1 is going to be 40 newtons. So my reaction at A is 40 newtons, and my reaction at C is 440 newtons.